In the farthest reaches of time, long after the last star has burned its final breath, the universe will fall silent. Galaxies will have faded into the black, their spiraling arms unwound by the expansion of space. The frozen remnants of worlds will drift through an endless night, unseen, unlit, unremembered. And yet, something will still endure. The great anchors of gravity, black holes, will remain. Born from the deaths of massive stars or from the collapse of unfathomable clouds of matter, they will outlive suns, planets, even the atoms themselves. They will be the final monuments of a once brilliant cosmos, their event horizons still holding the secrets of countless fallen worlds. But black holes are not eternal. Slowly, imperceptibly, they leak. A whisper of energy, Hawking radiation, escapes their edges, a ghostly exhalation that robs them of mass grain by grain. Over spans of time so vast they stretch meaning itself, the giants will fade. Supermassive black holes, weighing billions of suns, will shrink to the size of mountains, then to the size of dust, until, in a last, faint flicker of heat, they vanish. And when the final black hole dies, the universe will be left in a state it has never known before. A perfect, endless emptiness. No stars, no matter. Only the faint afterglow of that last breath racing outward into infinity. What happens then? Does the story of existence truly end in silence? Or is this death only the seed of something unimaginable, waiting in the stillness?
The black hole began not with a telescope, but with an equation. In 1915, Albert Einstein completed his general theory of relativity, a set of field equations describing how mass and energy curve the fabric of space-time. His equations predicted strange, extreme possibilities. If enough mass were compressed into a small enough region, the curvature of space-time could become infinite. Light itself would be trapped. Decades passed. Astronomers studied stars, nebulae, and galaxies, never suspecting that any of them might hide such objects. But in the 1960s, strange signals began to arrive from space. Some stars were seen orbiting invisible companions, moving at extraordinary speeds, as if held by something incredibly massive, yet unseen. Then came the discovery of quasars, points of light so bright they outshone entire galaxies, yet small enough to fit within our solar system. The only explanation that fit the data was a black hole, a supermassive one, millions to billions of times the mass of the sun, feeding on surrounding matter. By the late 20th century, the evidence grew overwhelming. X-ray observatories like NASA's Uhuru and later Chandra revealed the telltale signatures of matter heated to millions of degrees as it spiraled toward an invisible horizon. In our own galaxy, precise measurements of stellar orbits pointed to a single, inescapable conclusion. At the center of the Milky Way lurked Sagittarius A, a black hole with 4 million solar masses. Black holes were no longer hypothetical. They were real, and they were everywhere. Stellar mass black holes formed in the violent collapse of giant stars. Supermassive black holes anchored the cores of galaxies, and theories suggested there might even be primordial black holes, relics from the first fraction of a second after the Big Bang. Yet through all this, one question lingered in the background, an unspoken assumption. Astronomers believed that black holes, once formed, would last forever. In the cosmic ledger, they seemed to be permanent fixtures, swallowing matter and light, never releasing them. In a universe where stars age and die, black holes appeared eternal. That assumption would not survive the 1970s. At Cambridge University, Stephen Hawking was exploring the strange interface between quantum mechanics and relativity, two great theories that, like oil and water, resisted being fully mixed. Hawking was studying the event horizon as a one-way boundary.
When Stephen Hawking's equations first hinted that black holes could evaporate,
The idea seemed almost heretical. For decades, these objects had been considered the most permanent structures in existence. Stars aged and died, galaxies collided and unraveled, but black holes endured. They were the final, indestructible vaults of matter, locking away everything they consumed for eternity. In the great clockwork of the cosmos, they were the stones that never wore down. Now, that permanence was gone. Hawking's 1974 calculation forced the scientific world to confront a paradox. An object defined by its ability to trap light could, under the quiet influence of quantum mechanics, glow. Not with the furious blaze of a star, but with a faint, steady whisper of heat, a ghostly warmth bleeding away into space. The shock came not from the faintness of this radiation, but from its inevitability. According to the math, it could not be stopped. The event horizon, that perfect, one-way curtain, was not absolute after all. The union of relativity's curved space-time with the jittering vacuum of quantum theory left a tiny seam, a gap in the prison wall through which energy could escape. This was more than a curiosity. It was a challenge to some of the deepest laws of physics. One of these was the principle of information conservation, the idea that, in the fundamental equations of nature, no information about a system is ever truly destroyed. When a black hole consumed a star, a planet, or a single photon, that information was believed to be hidden forever behind the event horizon. Yet if the black hole eventually vanished into featureless thermal radiation, where did that information go? The possibility that it could be lost entirely struck at the heart of quantum mechanics. Richard Feynman's sum over histories, the Schrödinger equation, all rested on the assumption that nature keeps perfect account of its past. If black holes erased that history, the universe itself might be violating its own rules. Physicists called it the black hole information paradox, and it became one of the most persistent puzzles in theoretical science. The scientific shock was not about immediacy, it was about inevitability. In the farthest reaches of cosmic history, the universe would have no black holes left. The structures that had once been considered eternal anchors would be gone, their mass dispersed into a thin sea of photons and elementary particles, stretched thinner with each passing eon.
Deeper investigation. To follow the fate of black holes is to follow the fate of the universe itself. It begins with the present, a cosmos still ablaze with stars, and stretches forward into epochs so distant that even numbers strain to contain them. Physicists divide this long future into eras. The one we live in now is the stelliferous era, the age of light. Galaxies shimmer with hundreds of billions of stars, each pouring energy into space, each cradled by the dark grip of a supermassive black hole. This is the universe most people imagine when they hear the word cosmos, vast, bright, full of motion. But it is a young universe, not yet halfway through its story. In roughly 100 trillion years, stellar birth will cease. The raw material for star formation, clouds of molecular gas, will have been exhausted or locked into burned-out remnants. The last red dwarfs, those patient, ember-like suns, will slowly dim and die. When the final star flickers out, the stelliferous era will give way to the degenerate era. In that time, the only objects left will be the cooling corpses of the cosmos, white dwarfs, neutron stars, and black holes. Planets, if they still exist, will wander, orphaned, through interstellar space, stripped from their parent systems by gravitational tides. Collisions will be rare, events spaced by billions of years. The sky, once thick with constellations, will be black. It is in this dark age that black holes will begin to dominate the story. Every galaxy will still harbor its central supermassive black hole, some weighing billions of times the sun's mass. Scattered throughout the galactic remnants will be countless stellar mass black holes, born long before from the deaths of massive stars. At first, they will change little. For tens of trillions of years, they will continue to consume anything that strays too close, the occasional drifting star, an unlucky planet, or a fragment of matter from some ancient collision. Their event horizons will remain unchanged to the human eye, their darkness unbroken. But the clock of Hawking radiation will already be running. The mathematics is unforgiving. A black hole's evaporation timescales with the cube of its mass. The smallest black holes, if primordial ones from the early universe exist, would vanish first, their lifetimes perhaps shorter than the age of the universe today. Stellar mass black holes will take years to disappear. The supermassive giants will endure for 10,000, 100,000 years or more, their death throes unimaginably far in the future. Still, the end is inevitable. As they radiate, black holes will shrink. Their temperatures, inversely proportional to their mass, will slowly rise. At first, the radiation will be colder than the cosmic microwave background, the relic afterglow of the Big Bang.
It began as a solitary anomaly, a black hole that defied the quiet predictions of stellar evolution. But as weeks turned into months, the data did not fade into the margins of science. Instead, it multiplied. What appeared to be a single cosmic outlier began to whisper of a larger pattern, one scattered through the night sky, hiding in the depths where even light dares not linger. Astronomers searching old archives found echoes of the same impossible signature, gravitational effects too strong for any star-born black hole to produce. In distant X-ray binaries, in the dance of stars at a galaxy's heart, in subtle lensing distortions, bending light from galaxies billions of light-years away, the numbers whispered the same unsettling truth. This was not alone. The mystery deepened with every new observation. The black hole's spin seemed almost perfect, as if it had been polished by countless collisions, yet its environment showed no signs of the violent stellar carnage that such a history would require. Its mass placed it squarely in what astrophysicists called the pair instability mass gap, a range where, according to the most trusted models, black holes simply should not exist. In theory, stars between roughly 65 and 130 times the mass of the Sun should die in a spectacular thermonuclear unmaking, their cores destroyed in pair instability supernovae, leaving behind only gas and dust. No remnant, no singularity, no lingering shadow in space-time. And yet, this object lived. The paradox only grew sharper when researchers compared its chemical neighborhood to the models. Surrounding gas clouds showed elemental fingerprints suggesting generations of normal star formation, not the dense, ancient environments thought necessary for exotic black hole creation. If it had been born from the direct collapse of a primordial giant, there should have been a trail, heavier elements cast into space, shockwaves etched into the interstellar medium. Instead, the space around it was eerily unmarked, as though it had simply appeared. Even more disquieting was its location. It sat adrift in a stellar population far younger than itself, if its mass and spin were accurate indicators. This hinted at a story that began elsewhere, perhaps in the dense gravitational cradles of an ancient star cluster, before migrating there or being ejected into the region it now haunts. But how could such an object be expelled without tearing its surroundings apart? Some astronomers proposed a chain of mergers, black holes consuming one another in the tight confines of globular clusters until one reached forbidden mass. But the gravitational recoil from such mergers should send the resulting object hurtling into intergalactic space, not nestle it within a relatively calm stellar field. Others considered the possibility of a primordial black hole, a relic from the first seconds after the Big Bang, when density fluctuations in the newborn universe could have seeded singularities without the need for stars at all. If that were true, it meant humanity had stumbled upon an emissary from a time before time, a piece of the early cosmos that had survived for over 13 billion years. And if one such object drifted into view, how many more wandered unseen in the darkness between galaxies? As the possibilities widened, so too did the stakes. If such black holes were common, the entire model of stellar death and cosmic mass distribution would have to be rewritten. The gravitational wave signals that scientists were beginning to catalog from across the universe would need to be reinterpreted, their masses and spins no longer neatly fitting into the tidy evolutionary pathways sketched over decades. The deeper the investigation reached, the more contradictions emerged. Simulations meant to reproduce the object's birth failed unless one introduced new physics, exotic matter that resists collapse until certain thresholds or interactions with dark matter halos, altering a star's life cycle. But these solutions, while mathematically plausible, open doors to realms of speculation that even seasoned theorists approached with caution. There were whispers of stranger ideas still. Some suggested that the black hole was not an isolated object at all, but the visible signature of something larger, a wormhole throat, masquerading as a singularity, or the seed of a baby universe, whose event horizon marked the point where our space-time folded away from itself. These were ideas at the farthest edge of theoretical physics, where equations are delicate and untested, and where the line between profound insight and mathematical mirage is perilously thin. For now, the object remains silent, its nature obscured not by distance, but by the limits of human understanding. Telescopes could track its gravitational influence, measure the X-rays from matter spiraling toward its event horizon, and map the faint echoes of light bent around it, but none of these could tell the true.
The mystery had grown too large to ignore. The impossible black hole was no longer an isolated anomaly. It was a question mark carved into the fabric of the cosmos. The numbers could not be erased. The data could not be wished away. And so, reluctantly at first, the scientific community began to open the door to explanations that lived in the strange borderland between the plausible and the extraordinary. In that realm, theory is both compass and lantern, guiding inquiry, but also casting shadows where answers hide. The most conservative path began with direct collapse. In rare, almost mythical conditions, a star so massive, so swollen with its own gravity, might die without ever exploding. In such a death, no supernova would tear it apart. No blast would scatter its elements across the void. Instead, its core would fold inward in one continuous, unbroken plunge. The result? A black hole far larger than any born from the usual stellar deaths. Such a process would bypass the pair instability mass gap entirely. But the math demanded extremes. A star at least 100 times the sun's mass, shrouded in a metal-poor environment to prevent early mass loss, existing in an almost untouched corner of the galaxy. No such birthplace had yet been found near the black hole in question. Others looked to the dense hives of stars known as globular clusters. In these ancient, gravitationally bound spheres, stars dance in tight orbits, their lives measured in close encounters and violent mergers. It was possible, they argued, for small black holes to collide and merge again and again, each time swelling in size, until one reached forbidden mass. The gravitational recoil from such mergers, however, was a problem. The kick from those cataclysmic collisions should be enough to fling the resulting black hole into intergalactic exile. Yet here it was, resting quietly in its stellar neighborhood, as though it had never been disturbed. The bolder theories ventured further back in time, to the first seconds after the Big Bang. In that primordial chaos, the young universe was a roiling sea of energy and matter, dense enough that quantum fluctuations could magnify into titanic density peaks. Some of those peaks, according to primordial black hole theory, might have collapsed directly under their own weight, bypassing stars entirely. If our black hole were such a relic, it would predate the formation of galaxies themselves, a time capsule from the universe's first heartbeat. The implications were staggering. Such objects, if common, might account for part of the mysterious dark matter that outweighs visible matter by a factor of 5. They might be scattered like invisible anchors throughout the cosmos, their gravity quietly shaping the evolution of galaxies over billions of years. Yet primordial black holes remain a contentious possibility. Searches for them through gravitational microlensing, surveys have placed tight limits on how many can exist at certain mass ranges. Our anomaly, sitting precisely in the mass gap, slips between those constraints, neither proven nor excluded. Beyond these still plausible scenarios lay the speculative frontiers. Some theorists imagine that what we saw was not a black hole at all, but a wormhole mouth disguised by its gravitational signature. A wormhole could mimic the mass profile of a black hole while hiding a tunnel to another region of space or another universe entirely. The idea belonged more to the language of Einstein's field equations than to observation, for no telescope could yet distinguish between the two. And the universe offers no guarantee that such structures, if they exist, would remain stable long enough for us to find them. Others invoke the possibility of exotic matter, forms of mass energy not yet observed, whose pressure and density relationships differ from anything in the standard model of physics. Such matter could alter the collapse thresholds of massive stars, creating black holes where none should be possible. But until exotic matter is found, such proposals are no more than whispers in the theoretical dark. Perhaps the most unsettling idea came from questioning one of the most trusted pillars of modern science, Einstein's general relativity. In the unimaginable densities near a black hole's birth, could gravity behave differently than predicted? Some quantum gravity models suggest that at extreme energies, space-time might resist collapse, delaying or altering the death of massive stars. Others speculate that extra dimensions, hidden from our senses, could channel gravity in ways that subtly shift the limits of stellar collapse. If so, our impossible black hole might be not an outlier, but the first messenger of a deeper truth about the nature of the universe. For every theory, there were counter-arguments. Direct collapse lacked a matching stellar environment. Merger chains suffered from the recoil problem. Primordial origins wrestled with the scare.
Theories alone cannot solve a mystery like this. In the realm of astrophysics, conjecture without evidence is only a shadow cast on the walls of the unknown. And so, the search for answers turns from chalkboards to the night sky, from the language of mathematics to the instruments that can bend light, listen for space-time's tremors, and peel away the veil of distance. The black hole that should not exist has become a target for a new kind of hunt. It is not enough to study it in isolation. If others like it drift in the darkness, they must be found, their masses weighed, their spins measured, their histories teased out from the faintest clues. The work is painstaking, spread across continents, oceans, and orbits. The first sentinels in this search are the gravitational wave detectors, LIGO in the United States, Virgo in Italy, and Kagra in Japan. These colossal instruments, their arms stretching kilometers in length, are tuned to detect the faint ripples in space-time produced when black holes collide. Since 2015, they have heard dozens of such events. But now, their operators sift that cosmic symphony with sharper intent, searching for collisions whose masses fall into the forbidden pair instability gap. Already, hints have emerged. Events like GW 190521, a merger of two unexpectedly massive black holes, have forced astronomers to consider that the impossible might not be singular, but systemic. With each new observing run, the sensitivity of these detectors increases, opening a deeper volume of the universe to listening. The hope is clear: to catch one of these anomalies in the act of merging, revealing not just its size, but its ancestry written in the waveform. In space, other eyes watch with different senses. The James Webb Space Telescope, orbiting far beyond the moon's reflection, peers through cosmic dust with its infrared gaze. Its mirrors are not trained only on galaxies at the edge of time. Sometimes they turn to closer mysteries, studying the environments where massive stars live and die. By cataloging the birthplaces of the heaviest stars, Webb helps scientists understand whether the conditions for direct collapse black holes still exist in the modern universe. The Chandra X-ray Observatory and ESA's XMM Newton continue to map the high-energy light pouring from accretion disks around black holes. For an object like our anomaly, X-rays carry vital clues about how fast matter is spiraling in, how quickly the black hole spins, and whether it is feeding in ways that match or defy existing models. And in the radio spectrum, the Event Horizon Telescope prepares for future campaigns that may, one day, resolve details of black holes far smaller than the behemoths at galactic centers. Though our black hole lies beyond the EHT's current reach, its techniques, linking radio dishes across the planet into a single Earth-sized instrument, point toward a future where even stellar mass black holes might be imaged in silhouette. On the ground, an even greater machine is rising: the extremely large telescope in Chile's Atacama Desert. Its 39-meter segmented mirror will gather more starlight than any optical telescope in history. When it comes online, it will have the power to watch stars orbit invisible companions in distant clusters, measuring their mass with exquisite precision. Objects suspected of being in the mass gap will no longer be mere shadows in equations. They will be weighed and tested under the sharpest scrutiny. Meanwhile, surveys like Gaia and the Vera C. Rubin Observatory's Legacy, Survey of Space and Time, LSST, are sweeping the sky repeatedly, building an evolving map of stellar motions. A black hole reveals itself not by light, but by gravity, tugging on a companion star, shifting its path, pulling it in subtle arcs that, over years, become undeniable signatures. From this sea of data, candidates for mass-gap black holes will emerge, waiting for follow-up confirmation. Not all the work happens under the open sky. In vast computing facilities, simulations run for weeks or months, modeling the births and deaths of massive stars under countless variations, metal-poor gas clouds, binary star interactions, runaway collisions in dense clusters, even the gravitational influence of dark matter halos. Each run produces universes in miniature, where digital stars live and die, sometimes leaving behind black holes like the one that haunts us. The aim is to see which cosmic recipes, if any, can reliably produce such an object. Laboratories on Earth also play their part. Though no human machine can reproduce the death of a star, particle accelerators and high-energy experiments can probe the exotic states of matter that exist in their hearts. Quark-gluon plasmas, degenerate cores, and perhaps forms of matter that do not yet have names. If such matter changes the rules of collapse.
Far away, in a corner of the galaxy unseen by any human eye, a star has been burning for millions of years. It is no ordinary star. Its mass is immense, dozens of times greater than that of the Sun. For most of its life, it has stood in delicate equilibrium, a silent truce between two opposing forces. Deep in its core, nuclear fusion forges new elements, releasing energy that pushes outward. This radiation pressure is the only thing holding back gravity, the ancient architect of all structure. Without it, the star would collapse under its own weight. For millions of years, the balance has held, but even stars cannot burn forever. The core's fuel, hydrogen, then helium, then heavier elements, has been steadily consumed. Now, in its final stages, the star fuses silicon into iron. And here, nature's game reaches a limit. Iron cannot release energy through fusion. It is a dead end. Every atom of iron in the core is like a stone added to a great weight pressing inward. The balance is faltering. The star has entered its terminal phase. Inside the core, the temperature rises to billions of degrees. Layers of fusion shell burn furiously, but they cannot halt what is coming. The iron core grows, heavy and unyielding, until it reaches a critical mass, about 1.5 times the mass of the Sun. At that moment, the star's resistance shatters. Gravity takes command, and the core begins to contract. In a fraction of a second, it shrinks from the size of the Earth to the size of a city. Electrons are forced into protons, creating neutrons, and releasing a flood of ghostly neutrinos. From the outside, there is no visible change. Not yet. But within, the collapse is accelerating beyond imagination. Time itself seems to tighten. In just half a second, the core falls inward at 1/4 of the speed of light. The density becomes unimaginable. A teaspoon of this matter would weigh billions of tons. The outer layers, unaware of the trap they are falling into, continue to rush toward the center. And then a violent halt. The collapsing core slams into a wall of nuclear resistance. The neutrons packed so tightly they can go no further. The inward rush rebounds in an instant. A shock wave forms, racing outward, the star explodes. In one of the most violent events in the universe, the shockwave tears through the layers of the star, releasing more energy in a single moment than our sun will emit in its entire lifetime. For a few weeks, this dying star will outshine an entire galaxy. The radiation burns across space, carrying with it the heavy elements forged in the heart of the star and in the violence of the explosion itself: gold, platinum, uranium, the seeds of future planets, future oceans, future life. Yet amid the brilliance, something darker is forming at the heart. The collapsed core is too massive for neutron pressure to hold it. There is no force left in the universe that can oppose its weight. Gravity crushes the matter past the neutron stage, past the reach of known physics, into a singularity, an infinitely dense point where our understanding breaks. Around it, the event horizon forms. It is not a surface, not a wall, but a boundary in space-time. Anything that crosses it, matter, radiation, light, is gone from the visible universe forever. From the outside, the black hole is silent, invisible except for the fury of the gas and dust spiraling into it. But beyond the horizon lies a realm where time and space trade places, where the future leads only inward. If a distant observer could watch an object fall toward the event horizon, they would see it slow, its motion stretching into eternity. The light from it would fade and redden until it vanished entirely. But to the falling object, nothing unusual would be felt crossing the horizon, only the inescapable pull inward toward the singularity. Here, space is so warped that all paths lead to the same point. No speed, no light beam can escape. The collapse has reached its final destination. The black hole will endure for trillions of years, outliving galaxies, stars, and even the atoms themselves. Only through Hawking radiation, the slow leakage of energy predicted by quantum theory, will it eventually fade. But for now, it is young, and in the darkness at its core, the great collapse still echoes, a moment when a star's death became the universe's most perfect prison. The story of the great collapse is the story of transformation. A star's end is not an annihilation, but a reformation. Matter into energy, energy into space and time, the familiar into the unknowable. It is a reminder that even the most powerful lives end, but in their ending, they give birth to something new. The universe is not sentimental, yet it is never wasteful. And so in the silence of the cosmos, the black hole waits, a monument to the power of gravity, and a doorway to mysteries we are only beginning to imagine.
The cosmic whirlpool in the silent reaches of the universe, gravity is an artist. It draws spirals, arcs, and rivers of light across the black canvas of space. But there is no masterpiece more terrifying or more beautiful than the whirlpool that forms around a black hole. The black hole itself is invisible, a wound in the fabric of reality where light itself cannot escape. It offers no glimmer, no silhouette, and yet it does not hide. Around it, the violence of its hunger makes itself known. Matter, a hazy dust, and sometimes the shattered remnants of stars, spirals inward, tracing luminous arc as it falls toward the event horizon. This is the accretion disk, a ring of incandescent fury. It is not solid, but a storm of particles, each one trapped in a deadly dance, whipped into near-light speed by the black hole's gravity. In this disk, collisions are constant. Friction between layers of orbiting matter generates heat so intense it blazes in X-rays. Temperatures climb into the millions of degrees. Hydrogen atoms, stripped of their electrons, become a plasma, a sea of bare nuclei and free electrons, luminous and unstable. From a distance, it resembles a whirlpool of molten gold, glowing against the void. But unlike a whirlpool on Earth, there is no bottom to escape from. There is only the horizon. The black hole's gravity distorts not only space, but the path of light itself. Photons emitted from the far side of the accretion disk are bent around the hole, their trajectories curved into arcs that return to the observer's eye. The result is a strange doubling. The upper edge of the disk appears complete, while the lower edge, partly hidden, is echoed by a ghostly halo. This bending of light is gravitational lensing, predicted by Einstein's general theory of relativity and confirmed a century later by the Event Horizon Telescope's images of M87. Space is no longer a flat stage. It is a contorted arena where distance and direction lose their familiar meaning. And here, light has no single speed. To a distant observer, beams emitted from the inner edge of the disk slow, red-shifted by gravity's pull. Their wavelength stretches, their energy fades. Time itself runs differently near the black hole, and light carries the record of that distortion. Gas does not fall directly into the hole. It orbits first, like water circling a drain. The closer it comes, the faster it spins. At a certain radius, the innermost stable circular orbit, the spiral becomes a plunge. There is no path that leads outward again. For a black hole of stellar mass, this critical orbit lies just a few tens of kilometers from the horizon. For a supermassive black hole, it could be millions of kilometers out, yet still a fraction of its true scale. The matter here moves at a significant fraction of the speed of light. Centrifugal forces battle with gravity, delaying the inevitable. But energy is constantly lost, radiated away in heat and light. Each lap inward bleeds the orbiting gas of its momentum. The spiral tightens, the whirlpool deepens. When a star strays too close to a black hole, the encounter is catastrophic. Gravity tears it apart in a process called tidal disruption. The side of the star nearer the black hole is pulled more strongly than the far side, stretching it into a filament of incandescent gas. Half of this stellar debris is flung outward into space, while the rest joins the accretion disk. As it falls inward, it releases gravitational potential energy, converted into heat, light, and high-energy radiation. In some cases, the outburst is so luminous that it can be seen across billions of light years. Jets of plasma, launched from the black hole's poles by twisted magnetic fields, can reach thousands of light years into space. These jets, moving at relativistic speeds, carry away part of the energy extracted from the spinning disk. They are among the brightest phenomena in the universe, and yet their source, the black hole itself, remains unseen. There is a limit to how close matter can orbit before it must fall. At the innermost stable orbit, all trajectories lead inward. For a non-rotating black hole, this orbit lies at 3 times the radius of the event horizon. For a maximally rotating Kerr black hole, the innermost orbit can shrink to just above the horizon itself, allowing the disk to extend deeper into the gravitational well. Here, in the inner regions of the disk, the heat is so great that atoms disintegrate into their fundamental particles. The plasma's temperature exceeds that of the sun's core by hundreds of times. Magnetic fields writhe and snap, accelerating particles to energies far beyond those produced in Earth's most powerful accelerators. Time dilation is extreme. To an outside observer, motion slows to a crawl as the material nears the edge. To the particles themselves, their final moments pass in an instant, a fall that is timeless. The universe has music. It does not travel through air, nor through water, but through the very bones of reality. It is a song written in the fabric of space-time itself, a silent symphony that no human ear can hear. yet one that can shake the cosmos from one edge to the other. For centuries, the universe was thought to be silent. Light could be seen, heat could be felt, particles could be counted, but the stage upon which these actors played seemed immutable, unmoving. Then came Einstein. His general theory of relativity revealed that space was not an empty void, but a flexible medium, space-time that could bend, twist, and ripple under the influence of mass and energy. If space-time could bend, could it also vibrate? Could colossal events send out waves, not of sound but of geometry, spreading outward at the speed of light? Einstein's equations said yes, but the effect was so faint that he doubted it would ever be detected. A gravitational wave is not a wave in space. It is a wave of space. When massive objects accelerate, orbiting each other in a binary dance, colliding or collapsing, they disturb space-time, sending ripples outward in every direction. The most powerful sources are among the rarest: the merger of black holes, the collision of neutron stars, the collapse of stellar cores. These events can convert entire solar masses into gravitational energy in a fraction of a second, unleashing a vibration that can cross billions of light years without losing its form. And yet, by the time it reaches Earth, the wave has become so faint that it stretches and compresses space by less than the width of a proton. Consider two black holes orbiting each other. Their gravity locks them together, their orbital periods shrinking as they lose energy to gravitational waves. The closer they spiral, the faster they move. A cosmic pirouette accelerating toward an inevitable finale. In their final seconds, they may circle each other dozens of times per second, each orbit radiating gravitational energy into the cosmos. This crescendo builds until the moment of merger, when the two horizons touch, merging into a single, larger black hole. A final pulse, a ringing note called the ring down, spreads outward, carrying the last signature of the collision. Billions of years later, that same wavefront might wash over Earth, ever so slightly shifting the distance between two mirrors in a quiet laboratory. To hear this symphony, humans built instruments of extraordinary delicacy. LIGO, the Laser Interferometer Gravitational Wave Observatory, consists of two giant L-shaped detectors, each arm 4 kilometers long. A laser beam is split and sent down each arm, reflecting back and forth between mirrors suspended in vacuum. When a gravitational wave passes, it stretches one arm and compresses the other by a minute amount, changing the interference pattern of the laser light. The change is tiny, 1/10,000th the width of a proton, yet measurable. In 2015, LIGO heard the first confirmed note, the signal from two black holes colliding 1.3 billion light-years away. The detection lasted less than half a second, yet it confirmed a prediction made 100 years earlier. Gravitational waves come in many frequencies. The mergers of stellar mass black holes produce high-pitched chirps lasting seconds. Neutron star collisions sing a slightly higher tune, their aftermaths lighting up the sky with gamma-ray bursts, and colonnava supermassive black holes, millions of times the mass of the Sun, merge on far longer scales, producing bass notes that hum for years. These cannot be caught by LIGO, but instead are traced through pulsar timing arrays. Networks of spinning neutron stars whose radio pulses arrive with clockwork precision. When a gravitational wave passes between us and a pulsar, it shifts the arrival times of these pulses, like a drummer in a distant band playing just out of sync. By comparing dozens of pulsars across the galaxy, astronomers can detect this deep cosmic baseline. Unlike light, gravitational waves are not scattered or absorbed by matter. They can pass through entire galaxies, through the dense hearts of stars without weakening. This makes them messengers from places light cannot escape, from the very edge of black holes, from the hidden cores of supernovae, from the first moments after the Big Bang itself. One day, with sensitive enough instruments, we may hear the faint hiss of primordial gravitational waves, echoes from the first trillionth of a second after time began. When space expanded faster than light, in the burst we call cosmic inflation. The beauty of the gravitational symphony is that it unites the largest and smallest scales. It is born from the motion of objects across millions of kilometers, yet it is detected by measuring changes smaller than an atom's nucleus.
Time. It is the invisible current in which all things drift. To most, it feels steady, unchanging, a silent metronome ticking evenly across the universe. But in the deep gravitational wells of the cosmos, that steady rhythm bends, and near a black hole, it can almost stop. Everywhere in the known universe, time is measured by change. The vibrations of atoms, the swing of a pendulum, the turning of worlds. For most of history, it was thought to be absolute, a single, universal flow that carried all things together from past to future. But Einstein's general theory of relativity revealed a stranger truth. Time is not separate from space. It is part of a single, four-dimensional fabric, space-time, shaped and stretched by mass and energy. Where gravity is strong, time runs slow. This effect is tiny on Earth, but it is measurable. Clocks on satellites orbiting above our planet tick slightly faster than those on the ground, freed from a fraction of Earth's pull. It is not a flaw in the clock. It is a property of reality itself. Near a black hole, gravity's grip on space-time becomes extreme. Imagine a traveler drifting inward toward the event horizon. For them, each second feels no different from the last. Their heartbeat, their breath, the ticking of their onboard instruments, all unfold normally in their own frame of reference. But to an observer far away, watching through a telescope, the traveler's motion slows. As they approach the horizon, their descent seems to stretch endlessly. The light from their ship is red-shifted, its wavelength stretched until it fades into invisibility. From this distant vantage point, the traveler never truly crosses the horizon. They become frozen, suspended at the edge, their final moments stretched into infinity. This effect, gravitational time dilation, is not merely an illusion. It is a direct consequence of how space-time curves in the presence of mass. Every signal from the traveler, a flash of light, a pulse of radio, must climb out of the black hole's gravitational well. In doing so, it loses energy, shifting to longer wavelengths. The light reddens. The pulses arrive more and more slowly. Eventually, they stop arriving at all. The traveler is not destroyed in that moment from the distant perspective. They are hidden. Their timeline continues inside the horizon, but no message they send will ever escape to tell the story. For the traveler themselves, the crossing is uneventful. There is no visible barrier, no sudden change in the laws of physics. but the geometry of space-time has altered in a fundamental way. Outside the horizon, future means moving through time while still having freedom in space. Inside, future means only moving inward, toward the singularity. Every path, every possible motion leads there. From this point on, the difference between time and space begins to blur. The singularity is not a place in space that can be avoided. It is a moment in time that cannot be delayed. In theory, if a traveler were to orbit just outside the event horizon for a short time and then escape, they would return to the universe to find that far more time had passed for those outside than for themselves. For a black hole with the mass of our sun, this effect would be small unless the orbit was perilously close to the horizon. But around a supermassive black hole, millions or billions of times the sun's mass, the gravitational gradient near the horizon is gentler. In such an environment, one could orbit close without being torn apart by tidal forces, experiencing profound time dilation. A year for the traveler might correspond to decades, centuries, or even millennia beyond. The black hole becomes a time machine, not into the past, but into the far future. This possibility leads to a haunting thought. A traveler could journey to the rim of a supermassive black hole, linger for what feels like days, and return to find civilizations risen and fallen, stars burned out, galaxies transformed. The experience would be one way. They would not witness time passing quickly. Their own clock would tick normally. Only upon reuniting with the outside world would the difference reveal itself. In this way, black holes connect the intimate and the cosmic. A single heartbeat can be measured against the life cycle of galaxies. The slowing of time near a black hole is a mirror to another cosmic truth. In the earliest moments after the Big Bang, the opposite was true. Then the universe's density was so great that gravity's influence on time was nearly uniform everywhere. Only with expansion did differences in gravitational potential, and thus in time's pace, emerge. Today, black holes stand as pockets of the early universe's intensity, preserving regions where time's flow diverges sharply from the cosmic average. But no matter the scale, the end is the same. Space contracts, time collapses, and all paths converge to a single point.
Time is the quiet architect of the universe. It shapes the rise and fall of stars, the turning of planets, the birth and death of galaxies. Yet, in the presence of great mass, great speed, or vast distances, time does not behave as we expect. It bends, it stretches, and at its most extreme, it becomes almost unrecognizable. For most of human history, time was believed to be absolute, a universal metronome, ticking identically for all observers everywhere. It was the backdrop against which the universe unfolded. But this view began to fracture in the early 20th century. Einstein's theories of special and general relativity revealed that time is inseparable from space, woven together into a single malleable fabric. In this fabric, gravity is not a force pulling objects toward one another. It is the curvature of space-time itself, dictating how objects move. And as space bends, so does time. A clock in a deep gravitational well will tick more slowly than one in empty space. A traveler moving at a significant fraction of the speed of light will age more slowly than those who remain at rest. In the everyday world, these differences are imperceptible, but on cosmic scales, they become extraordinary. No place in the known universe distorts time more dramatically than the edge of a black hole. Here, the gravitational potential is so steep that time dilation becomes extreme. A star's light, emitted near the event horizon, is stretched to longer and longer wavelengths as it escapes, its energy drained by the climb. The rhythm of its flicker slows. To a distant observer, it is as if the star's heartbeat is fading into stillness. A traveler hovering just above the horizon of a supermassive black hole might experience hours while centuries pass in the galaxy beyond. The black hole becomes not just a gravitational trap, but a machine for projecting its surroundings into the far future. Gravity is not the only sculptor of time. Speed alone can change its flow. This is the domain of special relativity. As an object approaches the speed of light, its internal clock slows relative to a stationary observer. This is not an illusion, it is a measurable shift. The fastest spacecraft humanity has launched would produce only microseconds of time dilation in a human lifetime. But for a particle accelerated in a collider to near light speed, the effect is enormous. Muons, unstable particles that decay in millionths of a second, live hundreds of times longer when moving close to light speed. In the depths of space, around neutron stars or orbiting black holes, matter routinely moves at such speeds, locked into time frames utterly different from the universe at large. Imagine two twins. One remains on Earth, while the other embarks on a journey aboard a ship traveling at 99.9% the speed of light. For the traveler, the years pass normally, but upon returning, they find decades, centuries, or even millennia have passed on Earth, depending on the duration and speed of the voyage. This thought experiment, known as the twin paradox, is not a mere curiosity. It is a direct consequence of relativity, tested countless times in particle physics and in precision satellite measurements. In principle, such journeys could carry travelers into the deep future of the cosmos, skipping across epochs as easily as crossing a room. Neutron stars, the collapsed remnants of massive stars, are among the densest objects in the universe, so compact that a teaspoon of their material would weigh billions of tons. Their gravitational fields are intense enough to slow time measurably across their surfaces. If two identical clocks were placed, one on the surface of a neutron star, one far away in space, the surface clock would tick more slowly, falling behind by significant fractions of a second over short periods. For pulsars, neutron stars whose beams of radiation sweep across the sky with clock-like precision, these effects must be accounted for in astronomical observations. Time dilation is not only found in the intense gravity of collapsed stars or the high speeds of spacecraft. It was written into the universe from the very beginning. In the first instance after the Big Bang, the density of the cosmos was so great that gravitational time dilation occurred everywhere. In those conditions, fractions of a second saw changes more dramatic than billions of years of cosmic history today. As the universe expanded and cooled, gravity's influence on the global pace of time diminished. But in the densest pockets, the seeds of galaxies, the hearts of stars, local distortions continued to shape the rhythm of events. Relativity transforms time from a uniform stream into a varied terrain. In some valleys carved by gravity, time runs slow. On some peaks, far from massive bodies, it flows fast. From the perspective of a being living within one valley, another's clock may seem to race ahead. From the peak, the valley appears slowed.
The cosmos is silent, yet it speaks. Not in words, but in patterns, in harmonies of gravity and light, in the faintest whispers of radiation born billions of years ago. And somewhere in that silence, hidden between the tick of one moment and the next, lies an echo, a reflection of something far older than the stars. The question, older than time. For as long as there has been thought, there has been the question, why is there something rather than nothing? It is a question as old as humanity's first gaze into the night sky. As persistent as the pull of gravity itself, ancient civilizations carved their answers into stone and myth. The Egyptians imagined creation emerging from the primordial waters. The Greeks spoke of chaos birthing cosmos. In India's Vedic hymns, creation was a question even to the gods, a mystery without witness. But beyond myth and metaphor, the modern mind turns to physics, to mathematics, to the cold language of numbers. And even here, in the precision of theory, the echoes persist. The laws that shape galaxies also shape the mind, asking the question. The same constants that allow atoms to form allow neurons to fire. And so, the act of asking becomes a mirror, the universe contemplating itself. The echo in the equations. Einstein's field equations do not speak of meaning. They do not hint at purpose. They are pure geometry, the curvature of space-time in response to energy and mass. Yet their solutions reveal landscapes so strange they almost feel poetic. Singularities where time ends. Horizons beyond which events can never be known. The expansion of space itself, pulling galaxies away from one another faster than light can bridge. And in quantum mechanics, the rules grow stranger still. Particles exist in superpositions, probabilities solidifying only when observed. Some interpretations suggest that every outcome exists in its own branching reality, a cosmic library of all possibilities. To some, these are mere calculations. To others, they are philosophical mirrors. If every potential exists, then the act of existing here, in this universe, becomes the echo of countless paths unrealized. The human observer. In a purely physical sense, the universe needs no observer. Stars will form and burn, galaxies will collide, and black holes will consume without a single consciousness to witness them. But the emergence of life, and from it, consciousness, changes the texture of reality. Not physically, the laws remain the same, but in meaning. The echo acquires a listener. The philosopher Thomas Nagel once described consciousness as something it is like to be a particular organism. In the cosmos, consciousness is the rare phenomenon that allows the universe to experience itself subjectively. Here, in the human mind, the cold arithmetic of stellar nucleosynthesis, the fusion of hydrogen into helium, carbon, oxygen, becomes not just a process, but a story. The atoms forged in ancient stars become the hands that write the equation describing those same stars. The echo grows louder. Time's mirror. Physics teaches that time is not absolute. It can stretch, slow, or nearly halt under extreme conditions. But for conscious beings, time is not merely a coordinate, it is the medium of experience. The philosopher Augustine once confessed that time is obvious until one is asked to explain it. The same could be said of existence itself. In relativity, there is no universal now. The present for one observer may be the past or future for another. This absence of simultaneity suggests that the flow of time is not a property of the universe, but of perspective. And yet humans perceive life as a sequence, a chain of moments leading from birth to death. To see time as physics sees it is to realize that past and future may both coexist, like pages in a book. Consciousness moves through them as a reader moves through words, one after the other, while the story itself is already complete. What, then, is the echo? It may be the recognition that existence is not fleeting, but entire, that every moment ever lived remains. The illusion of edges. On a human scale, the world has edges: the horizon, the lifespan, the boundary between one thought and another. But the universe resists edges. Even the edge of the observable cosmos is not a wall, but a limit to what light has had time to reach us. Beyond it, space may stretch on indefinitely. Similarly, death may be seen as an edge, the final cessation of experience. But in the physics of information, there is no true destruction. The laws of quantum mechanics demand that information is conserved. Even if matter is swallowed by a black hole, its quantum state is thought to leave some imprint on the radiation that escapes, a faint, scrambled echo of what once was. If reality keeps every trace, then perhaps there are no absolute endings, only transformations, translations of one form into another.
Theories alone cannot solve a mystery like this. In the realm of astrophysics, conjecture without evidence is only a shadow cast on the walls of the unknown. And so, the search for answers turns from chalkboards to the night sky, from the language of mathematics to the instruments that can bend light, listen for space-time's tremors, and peel away the veil of distance. The black hole that should not exist has become a target for a new kind of hunt. It is not enough to study it in isolation. If others like it drift in the darkness, they must be found, their masses weighed, their spins measured, their histories teased out from the faintest clues. The work is painstaking, spread across continents, oceans, and orbits. The first sentinels in this search are the gravitational wave detectors, LIGO in the United States, Virgo in Italy, and Kagra in Japan. These colossal instruments, their arms stretching kilometers in length, are tuned to detect the faint ripples in space-time produced when black holes collide. Since 2015, they have heard dozens of such events. But now, their operators sift that cosmic symphony with sharper intent, searching for collisions whose masses fall into the forbidden pair instability gap. Already, hints have emerged. Events like GW 190521, a merger of two unexpectedly massive black holes, have forced astronomers to consider that the impossible might not be singular, but systemic. With each new observing run, the sensitivity of these detectors increases, opening a deeper volume of the universe to listening. The hope is clear: to catch one of these anomalies in the act of merging, revealing not just its size, but its ancestry written in the waveform. In space, other eyes watch with different senses. The James Webb Space Telescope, orbiting far beyond the moon's reflection, peers through cosmic dust with its infrared gaze. Its mirrors are not trained only on galaxies at the edge of time. Sometimes they turn to closer mysteries, studying the environments where massive stars live and die. By cataloging the birthplaces of the heaviest stars, Webb helps scientists understand whether the conditions for direct collapse black holes still exist in the modern universe. The Chandra X-ray Observatory and ESA's XMM Newton continue to map the high-energy light pouring from accretion disks around black holes. For an object like our anomaly, X-rays carry vital clues about how fast matter is spiraling in, how quickly the black hole spins, and whether it is feeding in ways that match or defy existing models. And in the radio spectrum, the Event Horizon Telescope prepares for future campaigns that may, one day, resolve details of black holes far smaller than the behemoths at galactic centers. Though our black hole lies beyond the EHT's current reach, its techniques, linking radio dishes across the planet into a single Earth-sized instrument, point toward a future where even stellar mass black holes might be imaged in silhouette. On the ground, an even greater machine is rising, the extremely large telescope in Chile's Atacama Desert. Its 39-meter segmented mirror will gather more starlight than any optical telescope in history. When it comes online, it will have the power to watch stars orbit invisible companions in distant clusters, measuring their mass with exquisite precision. Objects suspected of being in the mass gap will no longer be mere shadows in equations. They will be weighed and tested under the sharpest scrutiny. Meanwhile, surveys like Gaia and the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, are sweeping the sky repeatedly, building an evolving map of stellar motions. A black hole reveals itself not by light, but by gravity, tugging on a companion star, shifting its path, pulling it in subtle arcs that, over years, become undeniable signatures. From this sea of data, candidates for mass-gap black holes will emerge, waiting for follow-up confirmation. Not all the work happens under the open sky. In vast computing facilities, simulations run for weeks or months, modeling the births and deaths of massive stars under countless variations, metal-poor gas clouds, binary star interactions, runaway collisions in dense clusters, even the gravitational influence of dark matter halos. Each run produces universes in miniature, where digital stars live and die, sometimes leaving behind black holes like the one that haunts us. The aim is to see which cosmic recipes, if any, can reliably produce such an object. Laboratories on Earth also play their part. Though no human machine can reproduce the death of a star, particle accelerators and high-energy experiments can probe the exotic states of matter that exist in their hearts. Quark-gluon plasmas, degenerate cores, and perhaps forms of matter that do not yet have names, if such matter changes the rules of collapse.
Deeper investigation. To follow the fate of black holes is to follow the fate of the universe itself. It begins with the present, a cosmos still ablaze with stars, and stretches forward into epochs so distant that even numbers strain to contain them. Physicists divide this long future into eras. The one we live in now is the stelliferous era, the age of light. Galaxies shimmer with hundreds of billions of stars, each pouring energy into space, each cradled by the dark grip of a supermassive black hole. This is the universe most people imagine when they hear the word cosmos, vast, bright, full of motion. But it is a young universe, not yet halfway through its story. In roughly 100 trillion years, stellar birth will cease. The raw material for star formation, clouds of molecular gas, will have been exhausted or locked into burned-out remnants. The last red dwarfs, those patient, ember-like suns, will slowly dim and die. When the final star flickers out, the stelliferous era will give way to the degenerate era. In that time, the only objects left will be the cooling corpses of the cosmos, white dwarfs, neutron stars, and black holes. Planets, if they still exist, will wander, orphaned, through interstellar space, stripped from their parent systems by gravitational tides. Collisions will be rare, events spaced by billions of years. The sky, once thick with constellations, will be black. It is in this dark age that black holes will begin to dominate the story. Every galaxy will still harbor its central supermassive black hole, some weighing billions of times the sun's mass. Scattered throughout the galactic remnants will be countless stellar mass black holes, born long before from the deaths of massive stars. At first, they will change little. For tens of trillions of years, they will continue to consume anything that strays too close, the occasional drifting star, an unlucky planet, or a fragment of matter from some ancient collision. Their event horizons will remain unchanged to the human eye, their darkness unbroken. But the clock of Hawking radiation will already be running. The mathematics is unforgiving. A black hole's evaporation timescales with the cube of its mass. The smallest black holes, if primordial ones from the early universe exist, would vanish first, their lifetimes perhaps shorter than the age of the universe today. Stellar mass black holes will take years to disappear. The supermassive giants will endure for 10,000 years or more, their death throes unimaginably far in the future. Still, the end is inevitable. As they radiate, black holes will shrink. Their temperatures, inversely proportional to their mass, will slowly rise. At first, the radiation will be colder